Good morning, everyone. In our last class, we have been discussing about the applications of DSP. Now, coming to the next topic, classification of the signals. In the classification of the signals, if you see, we have several signal types, and we can classify it in this way. The first one is the continuous time and discrete time signals, analog and digital signals, real and complex signals, deterministic and random signals, even and odd signals, periodic and aperiodic signals, energy and power signals, and then lastly causal, non-causal and anti-causal signals. So today we will be looking into what are these types of signals. Okay, when we talk about this continuous time signal and discrete time signal, what happens is that any signal we take from the analog sensors, they are continuous time signals because those signals are being taken at all the time, so there is no discontinuity over there. Okay, now so this is an example of a continuous time signal. One of the example would be the acquisition of the temperature signals using the thermistors. Okay, now suppose this is the temperature recordings which we have got over the period of time. Now if I have to digitize it, so what we have to do, first we have to make the signal a discrete signal. Okay, so while we want to convert the signal into a discrete signal, we have to multiply the signal with an impulse train. So as the name suggests, impulse, it is having an amplitude of 1 at discrete point of time. Okay, so at time equal to 0, it will be having an impulse. At t equals to 1, it will be having an impulse. At t equals to 2, it will be having an impulse. And then when you multiply these impulses with the continuous time signal, you get some discrete points like this. Okay, so when the signal is not continuously varying with time, so when the amplitudes, they are not varying with time, continuously with time, then they are regarded as the discrete time signal. However, both the signals, they are regarded as the analog signals. Okay, in our last class we have discussed that analog signals are the signals whose amplitude varies in the range of -infinity to infinity. Okay, so even after the discretization, the amplitude of the discrete signals, discrete time signals, it may vary from -infinity to infinity, and due to this reason, both the types of the signals are analog signals. Okay, sometimes students do mistake. They sometimes think that continuous time signals are analogous to analog signals. This is because many of the time when we talk about the analog signals, we are basically talking about the continuous time signals, but the statement itself is incorrect. An analog signal is a signal whose amplitudes may assume any value in the range of -infinity to infinity. Okay, so a discrete time signal can also be an analog signal, right? Now these are the different ways you can represent the discrete time signals. So when we talk about the continuous time signals, the time operator is t. However, when we discretize the signal, this time operator, it becomes small n, and it may be represented in this equation form also, or because as I was telling you, we can have some values also, so we can represent the discrete time signals in this form also. Now over here, if you see, we have put a pivot underneath a value. So what does that mean? That means when you talk about any signals, so if it is n, which is increasing, we will be having a 0. So on the right hand side of the 0, we will be having all the positive n's. On the left hand side of the zeros, we will be having the negative n's. So how to mark the point n equals to 0? Okay, So this pivot, it allows us to mark n equals to 0. So wherever you will be finding that this pivot, that means this amplitude is at n equals to 0, then this one is at n equals to 1, n equals to 2, 3, 4 and so on. Similarly, on the left hand side, the n values will be minus 1, minus 2, minus 3, and at these time instances, these are the amplitude values. Okay. Now we can have various operations on the discrete time signals. Say for example, we can go for addition, we can go for multiplication, and we can go for the multiplication with the constant. In the second case, the multiplication of the two signals. Now how that is done? So let us take some examples. Suppose there are two signals x1n and x2n. x1n is given by 1, 3, 5, 4, 6. So we have seen that pivot is below 5. That means the n value over here is 0, 1, 2, minus 1, minus 2. Right? Similarly, we can define this x2n equals to 3, 2, 1, 4. Now let us first do the example of, let's say, yn equals to x1n plus x2n. So how to do that? So if you look over here on the right hand side,
n equal to 0, what do you mark?
it has to be marked. It has to be marked. Okay. So when we have this addition, so what we have to do, we have to match the origin points of both the signals. So here n equals to 0, 1, 2, minus 1, minus 2, right? So see, we have matched the two origin points, and then after you have matched it, then you can go for the addition. 6 plus 4, see 10, 5, 7, 6, 1. Okay, so this is the answer what we get. Now the next one is, say Zn equals to x1n multiplied by x2n. How to do that? If you see the multiplication, again you have to match the origin points and place the numbers accordingly, and then you can go for this thing. 5 multiplied by 2, 10. Okay, then 4, 24. Similarly on the negative time axis, 9, 0. So we have 9, 0, 4, 24. So 10 is having the pivot. So that means at n equals to minus 1, 0, 1, 2. Okay. Now then, if you go for any scalar multiplication, 4 into x1 n, you just multiply it, and wherever the pivot is, you just put the pivot. Okay. Now he has asked a very good question, that do we always put the pivot? The answer is yes. However, in some cases you will find, say for example over here, x3n equals to 5, 7, 2, 4, here there is no pivot. When there is no pivot given, that means the pivot is at the first instance. That means the signal is starting from n equals to 0, 1, 2, 3. Okay. Now coming to the analog and digital signals, I have already discussed about the analog signals. Analog signals can acquire any value from minus infinity to infinity. Okay, so any value means it can have 1.1 volt, it can have 1.111 volt, it can have 1.1111 volt, and so on. Okay, so on an analog scale, you can put without any approximation any value. Okay. Now, what about the digital signals? Digital signals are being generated from the continuous time signals by two processes. The first one is the sampling. I have already told that when you multiply an impulse train with the continuous time signal, you get the discrete time signal, and once you get the discrete time signal, that is again an analog signal. Now, in the discrete time signal, what we have done, we have discretized the signal in the time domain. Now in a digital signals, what happens is that the amplitude value should be discretized in the amplitude range. Okay, the amplitude values should be discretized, and the discretization of the amplitude values, it is regarded as the quantization. It is regarded as the quantization. What is quantization? It is nothing but rounding off of the signals, no components. Then let's go to the next slide. So now this slide is missing. Okay. So what happens over here is that, say for example, you are working in the range of plus minus 10 volts. Okay. So what you can do, say suppose you are having the 0, delta V value may be changed at an increment of 2, 4, 6, 8 and then 10. ऊपर मान लो 10 है कहीं पे. Similarly, minus 2, minus 4, minus 6, minus 8, minus 10. Okay. Now suppose there is some value of say 1 where you will be doing it, okay, or rounding it off. You have to round off, because if you see in digital signals the amplitude values can have only values of 0, 2, 4, 6, 8, 10, and in the negative side minus 2, minus 4, minus 6, minus 8, minus 10. Okay, if it is 1, so 50% hai, so 50% we round it off to 2. Now suppose if it is 0.9 volt you acquire, so where it would be rounded off? It would be rounded off to 0. Okay. Now this is basically when you are digitizing the signal, this kind of errors, it is regarded as quantization errors or rounding off errors. Okay. Now herein if you see the numbers, you are having this plus minus 10 volts. So the formula is delta V, it is equal to 2V by L. 2V by L. Okay. Here V is 10. So delta V we already know, it is 2 equals to 2 into 10. Okay. So L is equal to 10. So you see we will be having 10 intervals, 1, 2, 3, 4, 5, and in the upper side also we will be having 5. So we are having 10 intervals. Now if you want 20 intervals, L equals to 20, this delta V would be reducing. Okay. So in this way, by changing this L values, you can reduce the delta V values, and you can try to reduce the quantization error. The smaller the delta V, the lower will be the quantization error. Okay. L बोला ना, ये number of levels. L is equal to 10 मतलब यहाँ पे you see minus 10 to minus 8 one interval, the second interval, third interval, fourth interval, fifth interval. In the positive side also you will be having 5 intervals. 5 plus 5, 10. If you want 10 intervals, so 20 intervals, so what will happen? Everything is same, so your delta V, it would become 2 into 10 divided by 20, which is equal to 1 volt. So what you will be having? The intervals will be at a 1 volt interval. So the digital signals will be able to attain the values of 0 volt, 1 volt, 2 volt, 3 volt, 5 volt, like this onwards. Okay. So that's why you will see in most of the computers, previously it used to be 32 bits. Then why people wanted to have 64 bits? Okay, you will see the RAM. Previously, we used to have 4 KB RAM, 2 KB RAM. Okay. Previous to that, there was even 500 bytes RAM. फिर आया आपका 1 KB, 2 KB, 32 KB. Okay. So why these are increasing? Why, as the days are progressing, we are going towards more the higher specification? The reason being, we want these quantization intervals, delta V levels, to be as small as possible, so that the quantization errors it comes down. Okay. Now, real and complex signals. Real signals we always see in over time. So if you attach any sensor analog signal and then you try to just visualize that or collect it, you will be getting only the real values. You will not get complex values. However, when we talk about the complex signals, suppose you are having a signal and if you convert it into frequency domain by Fourier transform, then you get the signal components having both real and complex components. So the signals which are having both the real numbers and the complex numbers, they are regarded as the complex signals. Okay. Whereas any signal having only the real components, they are regarded as the real signals. Then deterministic signals and random signals. Deterministic signals are those signals which can be defined with a mathematical equation. Okay. So if you have a signal with which is following parabolic function, it is a deterministic signal. If it is a linear, if you have a signal which is following a linear function, it is a parabolic. It is a deterministic signal. Okay. So any signal which is following any mathematical equation, that is regarded as the deterministic signal. Why this is so? This ensures that at a particular point of time, what will be your amplitude values, you will be able to know. Okay. Whereas in the case of random signals, we cannot have an equation. Okay. So any signals which are not governed by any equation, which cannot be described by any mathematical equation, they are regarded as the random signals, and such signals, they are being characterized using probabilistic descriptions such as mean squared value, and so on. Okay. Then coming to the even and odd signals. So if you see the first thing, x of minus t equals to x of t. Okay, x of minus t is equals to x of t. So I will just give you an example. Take the example of a cos signal. Cos signal at 0 degree, what happens? It is having a value of 1 and it varies like this, and you extend it to the negative side. So what are the values at the positive side of the t? They are exactly equal to at the negative t values also. Okay, so that means x of minus t, that means amplitude at x of minus of t is equal to amplitude of the signal at time t. So if you see at 0 both are same. So say if this is 10, so at minus 10 also you are having the same value. So say if this is this amplitude, maximum amplitude is at say minus 20, then at plus 20 also you are having the same values. So when the amplitude values of the signals at t instance and minus of t instance are same, then those signals are regarded as even signals. On the other hand, when we talk about the odd signals, the value at t instance should be equal to minus 1 multiplied by amplitude at minus of t instants. When that happens, then it becomes an odd signal. The example is the sinusoidal waves. Okay, so here see in the, because period is same, so in the first year domain you are having a positive one, whereas in the negative domain you are having the negative amplitude. So x of minus t is equal to minus of xt. Okay. Similarly, for the discrete time domains also the same formula applies. Now this is what you can see. Anyway, so the first example is xn equals to sine of 2 pi n. I just showed you. It will be something like that. So here what we have, x of n is equal to sine of minus 2 pi n, which is equal to minus comes out minus of sine of 2 pi n. So minus of x of n. So we have xn equals to minus of x of n. So this signal, it is an odd signal. Okay. Similarly, for the cos 2 pi n, we, by the same logic, we have that this signal, this is an even signal, and the reasoning, mathematical reasoning, it has been given over here. Cos of minus 2 pi n is equal to basically cos of 2 pi n, which is nothing but your xn. So that is an even signal. Now coming to another example, xn equals to k multiplied by e to the power minus n u of n. So it is basically un means it is a right-handed signal. Okay. Now when you have a right-handed signal, here it has been told that find out the even component and the odd component of the signals. Okay. Now how the even component is given? Even component is given xen equals to half of xn plus of x of minus n, and odd component it is given by half of xn minus of x of minus n. Okay. So in the first case, when we talk about the even components, it is equal to half of k e to the power minus n multiplied by un. So this is the xn, so it goes just like this, and the second is x of minus of n. So this value remains the same. So this n, it becomes plus n over here, and u, and it becomes u of minus n. Okay. So what happens? This a component, if you see, it is positively sided signal, and this one, it is a u of minus n means your step function. It is a step function which is having an amplitude of 1 in the negative time axis. Okay. So u of n, it is a step function where your amplitude varies from n equals to 0 to infinity. Okay. So when you look into the B signal, it looks something like that. This is not 2 because 2 would come outside. Okay. So these are the values. Now you have got xn, you have got x of minus n. Now you add it up. When you add both of this, so half plus half, it becomes k. Okay, here what we have done, we have directly taken k by 2 and in both the cases, so you can keep it as k by 2, so xn by 2, and that's why it comes out to be k by 2. Okay, so either you can do it at a later stage, or you can directly include the constant somewhere. You are making it wrong. Both are different here. This one is a n varying from. Okay. Similarly, now you added these two up, so k by 2 plus k by 2 becomes k, and then you have this exponential signal. on the other hand, minus of x of minus n. So these values, they become negative. Okay, they become negative. So this one is the odd signal, odd component of the signal xn, xon, and this is the xen. Okay. Another example in the same way, we have the even component and the odd component. This is the even component, we have the odd component. Another some of the examples. Now say for example, you are given with two signals, xn, x of minus n. Okay. Now, yeah, over here we need to consider that here we have the pivot. Somewhere I missed the pivot, but in the x of minus n you can see the pivot. So here we should have the pivot. So we have the pivot. Okay, x of n, x of minus n, we are having the pivot. Then xn plus x of minus n, 4 plus 4, 8, 3 plus 2, 5. And just the way I showed you the addition, you do it. So you get this x of en, 2 of this one, 2 of x of en. So from here you can find out the x of en. Just divide the numbers by 2. Similarly, if you want to find out the odd components, you find out x of n minus of x of minus n, you get the values, and then for getting x of on, odd component of the thing, you divide all this number by a factor of 2. Okay. Now periodic signals and aperiodic signals. Now you all know sinusoidal waves are the periodic signals. So why they are regarded as periodic signals? They are regarded as periodic signals because x of t is equal to x of t plus capital T 0, which is regarded as the period of the signal x of t. Okay. So after every t0, the signal will repeat itself. Okay. So say take the example of the sinusoidal signals. So this is the t0. Now if I shift this origin from here to t0, see, the signal is repeating. Then if I again change it to 2 of t0, again the signal will be repeating. Similarly, the same thing will happen if you go to the negative time axis. Okay. Then any signal which is not following this equation, they are aperiodic signals. Okay, which is not following this equation, they are aperiodic signals. So this is an example of a periodic signal, continuous time domain, discrete time domain. Now, if I give you the equation of a signal, discrete time signal we will be discussing, because we are mostly interested in the digital time signal processing. So we will be dealing with only discrete time signal. So if I give you one signal, how to find out whether that is a periodic signal or not? Okay. So what happens over here is that we need to calculate capital N to find out whether the signal is periodic or aperiodic. So capital N is given by capital N is equal to 2 pi omega naught m. Okay, where m is a rational number. Okay, so xn is equal to, the first question is xn is equal to a to the power pi n. So in this equation, what is omega naught? Omega naught is basically the pi. Okay, so the capital N, it is equal to 2 pi by pi. Okay, I am using this equation, 2 pi omega naught is pi multiplied by m is equal to 2m. Now I said m should be a rational number. Suppose m is equal to 1. We are taking it as a rational number. Then what we get? N is equal to 2, which is also a rational number. Okay. So if m is a rational number, and due to that, if capital N is a rational number, then the signal is regarded as a periodic signal. Okay. Now coming to the next question, xn equals to cos of n into 1 by 8 minus of pi. What is omega over here? Omega is 1 by 8. Okay. So capital N is equal to 2 pi divided by 1 by 8 into m, which is equal to 16 pi m. Okay. Now if you see, if I put m equals to 1, 2, 3, whatever, this pi will be there. So the m will not be a rational number. Hence the signal xn equals to cos of n by 8 minus of pi, it is an aperiodic signal. Okay. Now coming to the next question, xn equal to sine square pi by 4 n. So if you see, we have broken it out into two components, x1n and x2n. I hope every one of you knows how it came from here to here. So it is basically the formula of the sine square theta. Okay. So from there, this x1n and x2n we got it. So now what we have to do, we have to find out the n values for both x1n and x2n. So over here, if you see, x1n, it can be written as half multiplied by 1 to the power n. So here n1 is equal to 1 because there is no omega naught associated over here. So that would be 1. On the other hand, for the x2n, what we get is that n2 equals to 2 pi by pi multiplied by 2m, which is equal to 4m, and considering m is equal to 1, we have n2 equals to 4. Now we have to find out n1 by n2 component, which is equal to 1 by 4. So we get 4 of n1 equals to n2, 1 multiplied by n2. So 4 of n1, this is equal to n. Now we have to take the LCM of the coefficients of both the n1 and n2, which is equals to 4. Okay. Now capital N for the signal xn, it is given by 4. Now this 4, it is a rational number, and since it is a rational number, it is periodic signal. Similarly, we can do the same thing over here with this example, where capital N is equal to n equals to 4. Next, coming to the energy and power signals. So in a signal with finite energy, it is regarded as energy signal, whereas a signal with finite and non-zero power, it is regarded as the power signal. So energy is given by this equation, A equals to integration of minus infinity to infinity x of t whole square modulus of x of t whole square dt, and energy is given in joules. Then power, which is basically the normalized average power, it is given by capital P equals to limit t tending to infinity 1 by t minus t by 2 to t by 2. Please see the limit. It is for a one time period. Okay, power is for a one time period. Okay, modulus of x of t whole square dt. Okay, so power, what is the unit of power? Unit of power is watt. Okay, energy, we have minus infinity to infinity. Power, the limit is for one time period minus t by 2 to t by 2. Okay. This is because it is considered that the energy signals, they are time limited signals, Okay, so they will end after a particular period of time. So if you take the limit from minus infinity to infinity, since they are time limited signal, they will end within a specific period of time. So you can do the integration, okay, for the whole time period from minus infinity to infinity. However, in the case of this power component, if you want to find out the power of the signal, if you do that, what happens? Power signals, they are not time limited signals. They are ever growing signals. Say for example, the example of the sinusoidal signals, whether it is a sine function or a cos function, they are going till the time infinity. Okay, so they are not stopping anywhere. So in those cases, if you do the integration, so what will happen? It will come out to be infinity, right? So because of this reason, for determining the power, the time integral which is taken is minus t by 2 to t by 2, that means one time period, and over here also 1 by t, it is considered to be because we are basically calculating the normalized average power, so this is the normalization factor. Okay, so this is in the continuous time domain. In the discrete time domain, same thing, you see, minus e equals to integration will be changed into the summation, so n equals to minus infinity to infinity, you have to do the addition, and normalized average power, over here you have to do the same thing, limit of capital N tending to infinity, 1 by 2n plus 1, summation of n equals to minus n to capital N, and then we are having modulus of x of n whole square. So these are some of the properties of the energy signals and the power signals. As I told you, for the energy signals, the total normalized energy should be finite and non-zero, whereas in the power signal, the total normalized power is finite and non-zero. Okay. On the contrary, if you see, the power of the energy signal is zero. Okay, the power of the energy signal, it should be zero, because at time tending to infinity, capital T tending to infinity, if you see, we are talking about capital T tending to infinity. What is happening? I said time tending the power signals are time they are ever growing signal, or not ever growing, ever continuous signal. Okay, so they are not band limited signal. So on the other hand, when you talk about this energy signals at time tending to infinity, it is zero, right? So power of the energy signal, it comes out to be zero. Okay, it comes out to be zero, because if you see, when we talk about these power signals, what we are doing is that when we consider the power signals, it is continuously going on over the time, and we are taking the energy signal. Energy signals are time limited signals. So in this case, what is happening? If you consider the whole time period, in that time period, the time limited signal component, it is very negligible, and due to that reason, when it is quite negligible in terms of the capital T tending to infinity, then it is called this. It is, if it is minuscule, then it is regarded as the zero power. Okay. On the other hand, if you talk about this normalized power of the power signal, it is finite and non-zero, because we are talking about the signal component within a particular range. However, the energy of the power signal is infinite, because the signal is infinitely continuing, and you have the integration changing from minus infinity to infinity. So everything is infinity. We have not limited that signal. Hence, the energy of the power signal, it would be infinite. So this is what it has been summarized over here. I think due to some reason it has been copied twice. Okay, I will take. So first question is xn equals to a into delta n. So it can be written in this fashion. So delta n, it is the direct impulse function. So it appears only at n equals to 0, and when you multiply the direct function with any amplitude, you get the amplitude value. So we got the amplitude value for n equals to 0. Okay. Now capital A equals to, so see, it is confined within a small region. So it is an energy signal. So what is the energy? Energy equals to summation of n equals to 0 to 0, because we have infinity to infinity, but the signal, it is appearing only at n equals to 0. So over here also we have n equals to 0 to 0 a square. So if a is finite, then a square will also be finite, hence it is an energy signal. Okay. Then we have xn equals to u of n. U of n, I have already told you, it will be having an amplitude of 1 till n tending to infinity. Okay. So it is given for n greater than equal to 0. So energy is, here is infinite. Okay, because it is continuing from 0 to infinity. So again, if you do the integration, it will be infinite. So power of this system is given by limit of n, capital N tending to 0, multiplied by 1 by 2 n plus 1, summation of n equals to 0 to n 1. Okay. Why? Because the value of un is 1, amplitude is 1. Okay. So if you see this one, next one, summation of capital n equals to 0 to capital N of 1, it is given by the expansion formula of capital N plus 1. Okay. Now from here we have p equals to limit of capital N tending to infinity, capital N plus 1 divided by 2n plus 1, and if you calculate this, you get capital P equals to half. So p equals to half and e equals to infinity. Okay. Now next it is xn equals to ramp of n. Ramp of n means xn equals to n. That means for at n equals to 0, the value of the amplitude would be 0. At n equals to 1, the amplitude would be 1. At n equals to 2, amplitude equals to 2, and so on. So that's why xn is equal to small n for n greater than equal to 0 and 0 for less than 0. Now if you find out the energy over here, it comes out to be infinite. Okay. Now there is an expansion series given over here, which has been used. This expansion series, it has been used over here. Okay. Similarly, if you talk about the power of the signal, it also comes out to be infinite. However, what was our assumption or the criteria for the energy signal? Energy should be finite and power should be 0, whereas in the power of the signal, we should have energy is infinite and power should be finite. Okay. However, this signal xn equals to ramp of n, it is neither following this energy criteria nor following the power signal criteria. So this signal is a neither energy nor power signal. Okay. Then again, the next one is xn equals to cos of 2 pi by 2 n. Herein this formula has been used. Cos square theta is equal to half of 1 plus cos 2 theta. So if you just put the values over here, you get this thing, and then you use this different series, like over here we have already discussed 2 of n, n plus 1, and then if you can find out the power and the energy of the signal. Energy is infinite because it is a cost function, and power, it comes out to be half. So it is a power signal. Another important case, this cos 2 pi n, summation of n equals to minus n to n cos pi n, it is basically 0. So this component has not been used in the subsequent sections. Now causal, non-causal and anti-causal signals. So any signal which is starting at t equals to 0 and is a right-handed signal, it is regarded as the causal signal. Any signal which starts at t or n equals to negative values of t or n, then they are called non-causal. Okay, causal is if the signal starts at t or n equals to 0 or positive values, then it is a causal. Non-causal is the starting of the signal should be in the negative halves, anywhere in the negative half. Okay, negative time domain, then it is a non-causal signal. And anti-causal is the opposite thing. It would start in the positive domain and then it will continue in the negative domain. So those signals are called anti-causal signals. Now coming to some useful signal operations. Time shifting, time scaling, time inversion, and then lastly combined operations. Okay, time shifting, when we shift the signal towards the right hand side, then it is called delaying. If we shift the signal towards the left hand side, then it is advancing. Okay. This delaying, it is given by, you see, t minus of a, and advancing, it is given by t of plus a. Okay. Now take this example. Fn equals to 1354 32512. Okay. Now we want to delay the signal by 2 units of time, f of n minus 2. So we have to move the origin value towards the right. So on other words, what we can say, we can move the pivot 2 values on the left hand side. Then only the origin will be starting at a later time. See, here the origin value, it is starting at a later value. So what we have done basically, from here we have changed the pivot towards the left hand side. Okay, so this pivot value, it needs to be shifted towards the here. So if you do this, then you get this value of n minus 2, so that will be delaying. And if you change the pivot value towards the right hand side, like over here from 3 to this thing, so this origin signal, it starts before the origin now. So this is called advancing. Yes. 3 to 5, because the value is 2 over here. So 1, 2, and since it is delaying, we are in the delayed signal over here, from the origin, the previous origin value, it should come on the right hand side. Okay, in the advancing, from the new origin value, the previous origin value should be on the left hand side, and the value over here is 3, so the 2, so we are moving the pivot 2 places on the right. Okay. Time scaling, we all do the same thing. In many of the YouTube videos you will find that it is written best watched at 1.5x. So what does that mean? You want to watch the video at a shorter time, so that is called the shrinking of the signal. So 80 means 1.5 time. Okay. Now if you change it to 0.5, same video you will watch for a longer time, so that is called the stretching of the signal. So see, this is the original signal. Shrinking, after shrinking by a, the signal is completing very fast. Whereas in the stretching of the signals, when it is say 0.5, it is basically say t by 2 basically. Okay. So when it is lower than 1, then it is called the stretching of the signal or dilation of the signal. Then time inversion, you just flip the signal components, positive वाले को negative में and negative signal components, it goes on the positive side. So see this negative component, it has come to the positive one, and in the other things in the lower half, if you see the positive signals, it has got signal components, it has got to the negative one. So across the pivot, you just reverse the signal. Okay. So let us see some examples. F of n equals to 3, 4, 5. This thing. F of 2n, how will you do? 2n means greater than 1. We are reducing some values. We are completing it very quickly. So some of the frames will be missed. So see 3, 4, this one 5. Okay. So f of 2n would be minus 1, 0, 1, 2. So this is basically n values, new n value for the f of 2n. Okay. Now for n by 2, you are delaying. So basically here there are 2. So see, after every 2 instances you should get this value. So we should interlace each of the signal with zeros in between. Okay. If it is by 3, then we have to interlace the signal components with that many number of the year. So that means if I have to go from 3 to 5, I have to do 1 jump, 2 jump, 3 jump. Okay. X of minus n, see ये जो 5 है, across the 3 pivot remains the same. 5 it comes over here, then 4 it comes over here, 3 it comes over here. Similarly this 2 it will come over here, 1. Across the center point you just rotate the signal. Then combined operations are there where we may perform x of 80 minus b. Okay. So let us take this example. F of n equals to this signal. So let us calculate f of minus of 2n minus 2. So from fn, first let us calculate f of minus 2. We calculated f of minus 2 over here. Then what is happening? F of 2n minus 2. That means एक value कट जाएगा. See, we are cutting one value each. So you get the 2n signal. Then there is a negative component. If you want to calculate f of minus 2n minus 2, then what you have to do? You just reverse it. Okay. पहले क्या करना है? First, whatever has been given over here, what is the delay function you see? Implement the delay. Then after delay has been implemented, you implement the scaling function, and once the scaling function is there, then you may go for the inversion, time inversion. Okay. So I will stop over here because